Okay, I'm going to work through example 1.6.1. This is on page 30 of the Mechanics of Flight, second edition by Warren Phillips. And he gives a hypothetical camber line defined by y sub c over c is equal to 4 ymc over c times x over c minus x over c squared. Okay, so ymc is the maximum camber, and if we do ymc over c, that's going to be in percent chord. Okay, so let's just get an idea of what this looks like. You can drop this into Excel or any other plotting package and look at what this camber line looks like. So on the x-axis, I'm going to put x over c. So that's going to go from 0 to 1 at the from the leading edge to the trailing edge. And then on the y-axis, we'll put y camber line over c. So this is all normalized by the chord. We'll see that it starts at 0 and is basically kind of a parabolic type of thing, where the maximum is ymc over c. So you can scale this up and down by changing ymc over c. That's simply the percent camber in terms of chord. Okay, so that's what this equation looks like, and I just think it's helpful to be able to kind of visualize what the airfoil looks like that we're working with. Okay, so we are asked to find alpha L0, that's the zero lift angle of attack, and the pitching moment about the quarter chord, Cm C over 4. Okay, so let's over here just plot what the lift coefficient for this two-dimensional section might look like as a function of angle of attack. Now, if the camber line just was right on the x-axis, meaning that there was zero camber. In fact, let's draw this out. If we have a symmetric airfoil, so pretend like that airfoil is symmetric, and we have an incoming velocity. Well, at 0 degrees angle of attack, it will produce zero lift because we have the same pressure distribution on the top as we do on the bottom. And so for 0 degrees angle of attack, we will get zero lift. Now, thin airfoil theory predicts that we'll have a lift slope or a change in lift with angle of attack of 2 pi. So we would see that the lift as a function of angle of attack would follow a line kind of like this. Well, we have camber in this airfoil by the amount of ymc. And of course, when ymc goes to 0, we'll be able to see that we get back results for a symmetric airfoil. But if ymc is positive, then we'll have positive camber. And it turns out that with positive camber at 0 degrees angle of attack, now let me just draw this airfoil here with some positive camber. So we've got some positive camber now. We'll draw the camber line in there, something like that. At 0 degrees angle of attack, we get some positive value of lift. Now, thin airfoil theory still predicts that the lift slope is 2 pi for any airfoil, and so we would find that the lift as a function of alpha is going to look something like that, which means that the zero lift angle of attack, which is this point here, and I'm sorry, my two plots are kind of running together. This is a separate plot over here. So this point right here is our zero lift angle of attack. That's the angle of attack where we will get zero lift on this airfoil. We see that it's got to be negative. In other words, the airfoil is going to have to be rotated down relative to the free stream velocity in order to produce zero lift. Okay, so it might look something like this, where this is our this is our angle of attack here, which is going to be negative, meaning that the that the free stream is coming in on the top of the airfoil instead of on the bottom of the airfoil. Okay, so that's the definition of our zero lift angle of attack. That's what we're trying to find here. And then secondly, we're going to try to find the pitching moment about the quarter chord. Okay, so let's look at our equations from thin airfoil theory. Now there's two different ways we can go about doing this. The first is that we can look at the lift equation. So CL can be written as, from thin airfoil theory, it is 2 pi times A0 plus 1/2 A1. Okay, so that's one way to write the lift coefficient. And that can be manipulated into a form that looks like this: 2 pi times alpha minus alpha L0. And the capital A0 is our first coefficient in the infinite series. And that capital A0 is defined as alpha minus some integral. Okay, I'm not going to write out the whole thing. And then the second coefficient, A1, which lift also depends on, is simply an integral. Okay, so when we integrate A0 and A1, we can plug those back into this lift equation here, and essentially alpha is just going to fall out here. So we're going to get alpha back here, and then this alpha L0 is basically the summation of these two integrals because we're adding them together here. And so another way to write alpha L0 is simply the summation of those two integrals, in a sense. So it's 1 over pi, it's the integral from 0 to pi of dyc dx times 1 minus cosine theta d theta. Okay, so you could solve this either way. You could either evaluate these two integrals here and plug them into this equation and then put it in a form that looks like this, subtract off the alpha, and basically whatever is in this location right there is going to be your zero lift angle of attack. Or you can just rearrange it from the get-go and show that alpha L0 is this integral right here. Okay, either way works. And there are advantages and disadvantages to both ways. Okay, the second thing that we're going to look at is the pitching moment. So Cm C over 4. So that's the pitching moment about the quarter chord. And the equation for the pitching moment at the quarter chord is pi over 4 times A2 minus A1. And so A2 is simply another integral over here, okay? So, and we also need A1 there. So one way to go about this is to solve all three of these integrals just up front and get values for each of them and then plug them into these equations here. We can back out what alpha L0 is here, and then we get directly what the pitching moment about the quarter chord is. Or another way is to realize that alpha L0 is the summation of these two integrals, which looks like this. And we can do the same thing with the pitching moment. We can just put those two integrals together, the A2 minus A1, and it can also be written like this. So we've got 1/2 the integral from 0 to pi of dyc dx times cosine of 2 theta minus cosine theta d theta. Okay, so we can solve it either way. We can either solve this equation or and this equation here, or we can solve all three of these integrals and just plug them into our basic equations here in terms of those Fourier coefficients. So either way works. You're going to get the same answer, and sometimes it's faster just to solve these three up front and then just plug them in. Sometimes it's better to solve them, these equations over here one at a time. So I'm actually going to take this second approach here where we're just going to plug it straight in for alpha L0 and solve this equation here. So let's start down that path. So the first thing, if we're gonna solve this equation here, this alpha L0 equation, what we need is a dyc dx, but that has to be in terms of theta. See, we're going to integrate in terms of theta, so we need to take this equation and first of all compute dyc dx. So dyc dx, and I'm actually going to take a shortcut here. That's equivalent to dyc over c dx over c. Okay, so we can actually take the derivative of this in non-dimensional form where we've non-dimensionalized it by chord, and that's pretty simple. So if we just look at this equation here and take the derivative of it with respect to x over c, what we're going to get is 4ymc over c times 1 minus 2x over c. Okay, so you could have also written that equation as yc and multiplied the c over. You would have gotten 4ymc times x over c minus x over c squared. So that's another way to do it. And then take the derivative of this, dyc dx, and then simplified. So you would have, gotten something here, and it would match this. But the shortcut is just to take the derivative in terms of x over c and y over c up front, and that's usually the easier way. So, okay, so now we have this equation, but this is still in terms of x over c, and we need it in terms of theta. So we've got our equation that tells us that x over c, or our transformation of variables to theta, is going to be equal to 1/2 times 1 minus cosine theta. Okay, so I can just plug this directly in there, and what I'll get is 4ymc over c times 1 minus, now the 2's are going to cancel, so I'm going to be left with 1 minus cosine of theta, like that. And so we can simplify again, and we'll get 4ymc over c times cosine theta. All right, so this is my dyc dx in terms of theta. Now, notice that we still have this constant here, ymc over c. That's just a constant that tells us how much camber is in this airfoil, okay? So it's just some constant that's going to float around in our equations for a bit, and then we can plug in different values for that at the very end and see how the zero lift angle of attack and how the pitching moment change with that maximum camber. Okay, so let's now plug this into our equation for alpha L0. So we're going to take this equation. So alpha L0 is equal to 1 over pi, the integral from 0 to pi. And I'm going to plug in for dyc dx, I'm going to plug in this relationship here, which is 4ymc over c cosine theta. And then the rest of that equation is 1 minus cosine theta d theta. All right, and I'm just going to rewrite this in a somewhat simplified form here. So we've got, I'm going to bring these constants out front. So we'll have 4ymc over pi c out front times the integral from 0 to pi of cosine theta. And I'm actually going to split this integral up into two integrals. So the first one is cosine theta, and then the second one is from 0 to pi of cosine squared theta d theta. Okay, so these are, I've just split that one integral up into the two different integrals. And so now I can integrate. So we've got 4ymc over pi c times the integral of the first, which is cosine. That gives us a sine of theta evaluated at pi and 0. And then we're going to subtract the integral of the second, So the integral of the second is a common integral that you can look up, but cosine squared of theta is simply 1/2 theta plus 1/4 sine of 2 theta. And I'm just going to bring in this minus. You notice we have a minus out front here. So I'm going to bring that into this term as well. So, and then we're going to evaluate that at 0 and pi. Okay. So, okay, so this is looking nice. So we've got YMC over pi c out front. And then the integral of the first, or this, so we've got sine theta, we evaluate that at pi, that's 0, sine of theta of 0, 0. So this term goes to 0. So that disappears. And then the second one, we've got minus 1/2 pi. So I plugged in the pi here, so we got a minus 1/2 pi, and then we're going to plug in pi here. Sine of 2 pi is 0. And then when I subtract off the values when I plug in 0, both of those are 0. So, so we're left with only this term from all that integration. And if I just simplified now, I get minus 2 YMC over C. So that is our zero lift angle of attack. So you can see that the zero lift angle of attack is negative. We've got a minus sign out front for positive camber. So if we plug in a positive number here for YMC over C, or percent camber, then we'll get a negative zero lift angle of attack, which makes perfect sense, right? We already discussed how we would expect for positive camber, we're going to have a negative angle of attack. And we also find that it is directly proportional, at least for this airfoil, it's directly proportional to the percent camber. So remember, alpha L0 is in radians, and it's directly proportional to the percent camber for this particular airfoil. Okay, so now let's look at our quarter-chord pitching moment, which is this equation here. So I'm just going to, let's see, I'll just draw a dividing line here, and we'll work down this on this other side. So the quarter-chord pitching moment, the equation for that, in terms of that integral up there, is 1/2 integrate from 0 to pi of dy c dx. Now I'm going to plug that in. So I've got 4 YMC over C cosine theta. Remember, we had to have that in terms of theta, so we're using that change of variables. And then we're going to multiply that by cosine of 2 theta minus cosine theta d theta. All right, and I can rearrange this a little bit. I'm going to pull this constant out front again, 4 YMC over C. So we're left with 2 YMC over C out front. And then I'm going to divide up the inner integral into 2. Again, I'm going to distribute cosine theta just like that. So in the first term, we'll have from 0 to pi of cosine theta times cosine of 2 theta. And then minus the integral from 0 to pi, and we've got a d theta in here, I forgot. And then we've got cosine squared of theta d theta. Okay, so so I'll just come down here to YMC over C, and the integral of that first term, and this is one reason why these series are so nice to work with, or this change of variables in theta instead of x over c. But the integral of a cosine theta times cosine 2 theta, actually the rule is that if you have the integral from 0 to pi of cosine times m theta, cosine times n theta, d theta, this will always equal 0 if m is not equal to n, okay? So in our case, we've got a 1 right here, cosine of 1 theta. times cosine of 2 theta, and m and n are not equal. And so when we integrate from 0 to pi, and that's this rule here, if we integrate from 0 to pi for that equation here, then it will equal 0. So again, this is one of the nice benefits of working in these in this change of variables. Okay, so that first integral is 0, and then the second integral is actually identical to this guy right here. From 0 to pi, cosine squared of theta d theta. We've got that negative sign out front, so we can just plug that in. So it's minus 1/2 theta minus 1/4 sine of 2 theta. And we're going to evaluate that from 0 to pi. And so let's see, that's going to give us 2ymc over c times, and now we're just going to have a minus 1/2 pi in here. The rest of those terms go to 0. And so our final solution is negative ymc over c times pi. So let me make sure that's right. Yeah, that looks right. So that is our cm c over 4, our pitching moment about the quarter chord. And again, this is directly proportional to, well, first of all, it's negative, right? For positive camber, our pitching moment is going to be negative, so it's going to be a nose down pitching moment if we have positive camber. And that pitching moment is directly proportional to the amount of camber we have, that ymc over c. So let's see, there's one other thing I wanted to mention here. Oh yeah, if we plug in 0, so what if ymc over c is 0, that gives us a symmetric airfoil, and that gives us alpha L0 equals 0, and cm c over 4 equals 0 as well. So that's a nice check. If we plug in a 0 here for the camber, then we produce a symmetric airfoil, which means that the zero lift angle of attack is going to be 0. In other words, the lift, this lift here will pass right through the origin. And then the pitching moment is also 0, which makes perfect sense. The pitching moment about the quarter chord, because the pitching moment about the quarter chord doesn't change with angle of attack according to thin airfoil theory. And so if you look at that pitching moment at 0 degrees angle of attack for a symmetric airfoil, the pitching moment would be 0. And because it doesn't change with angle of attack, then it would be 0 at every angle of attack. Now that's within the approximations of thin airfoil theory. It says that the quarter chord is your aerodynamic center, and so the pitching moment does not change with angle of attack. And so the pitching moment for a symmetric airfoil would be 0 at the quarter chord.